De hoy martes voy a dejar a Paula que haga la presentación del invitado que tenemos hoy en el seminario. Entonces, Paula, adelante. No sé si me escuchaste, Paula.
Paula.
Sí, Paula. Paula, ¿no escuchas?
¿Ya me escuchan?
Sí, sí. Ya había dicho que ya íbamos a empezar el seminario.
Ay, Luis, creo que no te escuchamos nosotros.
Bueno, pues entonces empezamos el seminario, dejamos que Paula...
¿Ustedes me escuchan a mí?
Sí, ahora sí.
Sí.
El invitado, adelante, Paula.
Si quieren yo empiezo porque no te escucho, Luis, pero imagino que estarás diciendo que podemos empezar, ¿sí? Perfecto. Okay, it's a pleasure for me to have here today at the Condensed Matter Seminar to our guest speaker, Pedro Gonçalves. Dr. Pedro Gonçalves already. I met Pedro when I visited Universidad Federal de Minas Gerais in 2019. Back then he was a graduate student, a PhD student in that institution. And since then, we started a very beautiful collaboration for measurements and understanding of tantalum tellurium 4, for which he has beautiful results. Pedro did his undergraduate, master's, and PhD at this university at Minas Gerais in Belo Horizonte, Brazil. And he's about to start a postdoc position, and congratulations for that, Pedro, at Universidad de Paris-Saclay, with a world-renowned scientist, Andrés Santander Ciro, and he will be doing ARPES measurements in a variety of materials. So I guess he will talk to us a little bit about his experience with ARPES and with other microscopy techniques for correlated materials. So thanks for being here, Pedro. We cannot hear you, Pedro, if you can activate your microphone.
Thank you for inviting me. Okay, can I start sharing?
Yes.
First, thank you for inviting me to the seminar here on Andes. A special thanks to Professor Paula Giraldo for inviting me to give this talk. As she said, I'm from the Federal University of Minas Gerais in Brazil, and I will talk about what I'm doing on the last 3 years on my research, which is the spectroscopy of topological materials. Focusing on two kinds of spectroscopy that I will explain here, which are photoemission spectroscopy and tunneling spectroscopy. First, to give a little review on the subject of spectroscopy, we know that from the Schrödinger's equation, we can retrieve the relation between the energy and momentum of the electrons inside the solid. There are from get this important relation here, we can use calculations to get this relation. And here there is an example of an electronic band structure calculated with a density functional theory of an insulator here. But also what I study here is we can retrieve this relation using some experiments that I will explain in a minute. Here's an image of angle-resolved photoemission spectroscopy of Bismuth Selenide taken at the Brazilian synchrotron in Campinas, which is the way to relate the energy momentum relation by the calculations and experiment. So I split this talk here in 2 parts. In the first part, I will talk about what are topological materials, especially topological insulators, and how to measure these topological materials. I will focus in these 2 spectroscopies with Scanning Tunneling Microscopy, and spectroscopy, and the Photoemission Spectroscopy, focusing on unresolved photoemission spectroscopy. And on the second part, I will present 3 works that I did on this subject, which say the formation of bismuth selenium phases upon the annealing of the bismuth selenide, and the quaternary topological insulator bismuth antimonium selenium 2.5 tellurium 0.5, and the topological states in the CDW compound tantalum tellurite. So to understand what are the topological materials, first we need to get used with the concept of topology. Topology is the branch of mathematics that studies the properties of objects that are preserved through deformations. What that means, with topology, we can classify the geometrical objects by the number of holes they have. For example, here we have an sphere and a cube and a disk, and this all these 3 figures, they don't have holes on the surface, which means that they have the genus equals to 0. So objects that have the same genus, they are called the topological equivalent. But we can have a figure like that, which is kind of a donut that have genus equals to 1. And we have, for example, 2 holes, we have a genus equals 2. And the objects with different genus, they are called topological distinct. The thing here is that objects with different genus, they cannot be transformed into each other without the creation of a hole on the surface. And how to calculate, how to distinguish between these objects, how to calculate the number of holes of a given surface. For that, we have the Gauss-Bonnet Theorem, which is, we take a surface here, and we calculate the Gaussian curvature, or the integral, the surface integral of the Gaussian curvature of an object. And when we calculate here, we have an integer number here related to the genus of the object. So this concept of topology, then in condensed matter physics, is a kind of similar. Here we have the topological classification of insulators. We have, for example, on an electronic bandstructure here of an insulator, and we have this formula here to calculate. We have this quantity here, this F here is called the Berry curvature, which is a quantity that we calculate on the quantum states of our system, of our solid. And if you integrate this Berry curvature over the first below 1 zone, we have a number, an integer number here, which is called the chair number. So in that, if the chair number of our system is equal to 0, we have an ordinary topological insulator. And if it's different from 0, we have a topological insulator. That's this formula is pretty similar to the Gauss-Bonnet theorem here. And it have the same property. So if we have insulators with different genus, they cannot be transformed into each other unless the energy gap is closed. What that means, if we have a system here with a given electronic band structure and another system with a different chair number, to transform from this through this other one, in some time when you do the transformation, the energy gap of the system will close and it will not be an insulator anymore. So the question that remains is, what happens in the interface when we put 2 materials with different chair number together? So when we put, for example, 1 equals to 0 and 1 equals to 1, in the interface of them, if they have a chair number, a different chair number, on the interface, the gap should close. So just in the interface, it will appear some states here that will do this connection here. So at the interface, there is states on the gap, and the outside of the interface, there is no energy states crossing the band gap. So with that, we can define what are the topological insulators. Topological insulators are materials that are insulators in the book, but metallic on the edge or the surface, depending on if the material is a 2D material, the metallic states are on the edge, and if they are 3D material, the metallic states are on the surface. We have, for example, here a figure of a conduction band and valence band of a given insulator here, and just on the surface, we have these states crossing here. And if we look on different positions of momentum, we can see it for a 3D crystal, we have 2D states, and we'll form what we call the Gerais cone. Here, this states here, when we rotate, we form the Gerais cone. And the Gerais cone is the signature of the topological insulators. Here we have, for example, here the most known topological insulator, which is Bismuth Selenide. Here we have theoretical calculations here when you have the bands here of the material, and you have the states crossing here the band gap, and here we have ARPES images of the same structure as here. So after this little introduction about the topological material, let me talk a little bit about the experimental techniques that I use to study these materials, these topological insulators. So the first of them is the Scanning Tunneling Spectroscopy, which is based on the phenomenon of quantum tunneling. The quantum tunneling, as remember, if you have a waving function here, and this waving function faces a potential barrier here that have more energy than the energy of the waving function here. Classically speaking, it's forbidden to the waving function to be in this region here, but as a quantum effect, if depending, there is a probability that there is that the particle could be here, but depending on the size of this potential barrier here, there is a probability that the waving function here could go on the other side. This is the tunneling, the quantum tunneling phenomenon, when you can pass through a barrier that's have more energy than the particle. Using this phenomenon, they constructed what we call the Scanning Tunneling Microscopy. What is that? We have a chip here, and we have a sample, a metallic sample, and when we approach the tip of the sample here we have a vacuum, which is a potential barrier here, and when the tip is closer enough to the sample, there is the tunneling of the electrons from the chip to the sample. And if we apply a bias voltage here between chip and sample, we can control a tunneling current between the chip and the sample. With that, they constructed a microscope. So what is an STM machine does is that there is a piezo scanner here attached to the tip, that the tip can move in all directions here. And with that, if you have a feedback system here, we can try to maintain the tunneling constant, and we'll the current, the tunneling current constant, and with that we can make an image of the topography of the sample. And here there is an example of STM data. Here is the honeycomb lattice of graphite, and here there is an image, a picture of the equipment on the nanoscopy UHV laboratory in UFMG. Here we have the STM. Our STM can go to low temperatures. Here we have a liquid helium viewer here to freeze the equipment, and you also have a lead here to make some preparation on samples. But the most powerful thing that this kind of equipment does to us is in the case of a spectroscopy is the Scanning Tunneling Spectroscopy. What is that? Instead of maintain the current constant and move the chip to have the topography, now we will stop the chip, and then we apply, we change the bias voltage on the chip, and we measure the current that goes over the change of the bias voltage. So we have this IV curve on the certain points that we want on the sample. With this IV curve, we do the derivative, and we have the IDV curve. Here's an example of the IDV curve made for with STS spectroscopy. And the thing is, this quantity here, it's a picture of the density of states of the sample on this on the local that you did the measurement. We know that the current here is given by the integral here with these two quantities, which is the density of states of the tip and the density of states of the sample. We can treat the density of states of the tip as a constant here. And when we do the derivative here, we have that the IDV curve is directly proportional to the density of states of the sample. Here, for example, is the electronic density of states of graphene here. That's it's easily to get when you measure on the STM. So the other kind of spectroscopy is the photoemission spectroscopy. The photoemission spectroscopy is based on the photoelectric effect. The photoelectric effect, as we know, everybody should know, consists of, we have a metallic sample here, and we shine light on this sample, and this light is capable of ejecting electrons from the material. Almost 20 years later of that discovery, Einstein explained this phenomenon using this energy conservation formula here, when we have that the kinetic energy of the photoelectrons is equal to the energy of the photons that goes on the sample, minus the work function, which is a constant that it's a characteristic of each material, minus the energy of the electrons inside the solid. So we have these two quantities here that comes from the experiment that we know. We measure the kinetic energy, and we know the energy of the photons here from the frequency of the light. And we have these quantities here that comes from the material. So what we can do is that when we measure the kinetic energy, and we know all these quantities here, we can, from the kinetic energy of the photoelectrons, we can know the energy of the electrons that are inside the solid. This is what we call the photoemission spectroscopy, when we use light to have information about the energy of the electrons inside the solid. The angle resolved photoemission spectroscopy adds another thing to this recipe, which is the momentum. So we have the photon source, and we have the electron analyzer here, but this electron analyzer is capable of measuring not just the kinetic energy of the electrons, of the photoelectrons ejected here, but also the momentum of these electrons. Using these formulas here, we can see that the momentum of the electrons that comes inside the electron analyzer, they are related to the kinetic energy of the electrons that we can also measure here, and to the angles of the electron that comes here. So what we do in an ARPES experiment is that the sample is attached to a manipulator here that we change the positions of our sample, and then you can also rotate the sample in every directions here to change these angles here, and you can make an image, a 3D image of the relation between energy and momentum of a sample. Here we have, as I said, the Einstein equation here that relates the kinetic energy to the binding energy, and you can also relate the momentum of the electrons inside the solid, with these momentums here that are measured. So what we measure is the kinetic energy of the electrons and the angles that the electrons goes inside the electron analyzer. And from these measures, we can obtain the information which is the energy of the electrons inside the solid, which is called the binding energy, and the momentum of the electrons inside the solid. So here is an example of an ARPES data, as I showed before, is the Gerais cone of bismuth selenide. And here's a picture of the experimental setup of the PGM line on the Brazilian synchrotron located in Campinas. So from that, I'll start the second part of this presentation, which is the projects that I did on the last 3 years, including in my PhD, that we use this spectroscopy, the powerfulness of this kind of a spectroscopy. The first one is the formation of bismuth selenium phases upon the heating of bismuth selenide. So what we have, we know that the bismuth selenide is composed by quintuple layers of selenium, bismuth, selenium, here, what they create this structure here that we call quintuple layers. But the thing is that when we heat this material here, this sample here, the selenium here, because it's lighter, they start to flow. So what happened is that there is the formation of bilayers of bismuth on the sample when we heat to a given temperature higher from almost 400 Kelvin. So we know then that the growing process suggests that the phase formation of the system, it goes like this: a combination of quintuple layers of bismuth, bismuth 2, selenium 3, and bilayers that bismuth 2. Here we have an image, an example here, an image from using X-ray diffraction. Here we try to estimate over the temperature the formation of the new phases of bismuth selenide. Here we can see that there is a great change from bismuth 2 selenium 3 to bismuth 4 selenium 5, which is the unit cell of bismuth 4 selenium 5 is the combination of one quintuple layer and one bilayer. If we continue heating the material, it will start to form another kind of structures that we can see here. There's a little bit of PI1, SI1. So what we did that now we take this sample and put on the STM to study the dynamics of this BI4 SCF5 formation using STM and STS. So the STM results, here we saw that the bismuth 4 selenium 5 appears as nanograms in the matrix of bismuth 2 selenium 3. Here we have, for example, here an STM image of atomic resolution of bismuth 4 selenium 5, and here is an example of a grain that you can find on the sample. We saw then that there are two patterns of structures from this image found on the sample. In a region there is only a bismuth 2 selenium 3, we can see that we always have steps of 1 nanometer here. But when we go to regions when we have the other structures, the bismuth 4 selenium 5, we can see, for example, here that we have steps that are less than 1 nanometer. For example, here we have 0.4 nanometers, which is related to bilayers of bismuth. So then we use the STS, Scanning Tunneling Spectroscopy, to differentiate between these two phases. So we took a grain here, like the other ones, and then this grain is good because we have three types of terminations here. We have a termination here of bismuth 2 selenium 3, and we have bismuth 4 selenium 5 with two different terminations, with one termination with a bilayer of bismuth and one termination with a quintuple layer. The result is here. We have what we expected for the Gerais cone on bismuth selenide here on black. And we have the other two structures here. The bismuth for selenium 5 with determination of a ketopole layers is pretty much similar to bismuth to selenium 3, but with a little bit of the metallic character of this structure here is increased in related to the 2-3 sample. And we have this one that's pretty much different for the other ones with the bilayer termination here. Another thing that we could do using STS on our sample is that we can try to make a line spectroscopy here. What that means, you can do an spectroscopy on each point here, approaching the nanograin, so you can see the changes on the density of states of the sample when we go from bismuth to selenium 3 to bismuth for selenium 5. And we can see here that the sample, the new characters of the sample starts to appear, and the sample becomes more metallic when we enter the bismuth for selenium 5. So this was an example of using the STS spectroscopy to differentiate between two kind of structures in a material in the nanoscopy level. The other two works that I will present is more like it's related to the photoemission spectroscopy, which is a technique that we don't go to small structures like on the nanoscale. We shine a sample on over a very wide region, but you give two different kind of information, but the thing is that the technology here is going on the path that now we have synchrotrons over the world that we can measure photoemission just on small spots like we have on STS. So the second work is the quaternary topological insulator bismuth antimonium selenium 2.5 tellurium 0.5. So the bismuth selenide is part of a class of materials that are called the bismuth chalcogenized topological insulators. They all have the same structure here of quintupole layers, but different from bismuth selenide. The blue atom here could be from selenium on tellurium, and the red atom here can go from bismuth or antimonium. The main examples here are the bismuth selenide, bismuth tellurite, antimonium tellurite, and antimonium selenide. We saw that from these three here, we have topological insulators. So we can see here the states crossing the band gap here, but the antimonium selenide is not a topological insulator, just a regular semiconductor. We can also have a mixture of these elements, and we can have samples with three of these elements here. For example, here we do the changing of selenium and tellurium ratio here on the bismuth selenide system here, and here we have image of ARPES of the Gerais cone. What happens with the Gerais cone when we change selenium for tellurium. And we also have here an ARPES work here when we change the amount of bismuth and antimonium and maintain the tellurium here. We can observe the changes on the surface on the surface states of bismuth tellurite also. Before goes to the ARPES results, we did a chemical analysis. Here we have an electron microscopy image here of a grain in our sample here, on a powder sample here, and you can see that the four elements are uniformly distributed in our sample. We also have an X-ray photoelectron spectroscopy here. We did an X-ray electron spectroscopy here on the sample, which is we did a photoemission spectroscopy using a X-ray tube here, and we can see that we can identify the peaks of each element of our sample here. And from each peak here, we try to analyze the using a Gaussian analysis here. We can fit a Gaussian on each peak here, and we try to estimate the amount of each element on our sample. Here we have the estimated using this analysis here, we can retrieve the estimated stoichiometry of bismuth 1, antimony 1, selenium 2.5, tellurium 0.5. The ARPES results starts with we put two samples on the ARPES. We have the bismuth selenide, and we have the quaternary sample with the 4 elements. And we can see here that from bismuth selenide, the distance here from the Fermi level to the Dirac point here is 0.37 electron volts, and on the quaternary sample is 0.22 electron volts, which means that the addition of antimony and tellurium on the sample creates a p-type doping on the positively doping of 0.15 electron volts on the bismuth selenide. Another thing that we can do using ARPES is that when we can take, this is an image of energy over a certain angle here, but we can rotate the sample and measure all pictures with all different angles, and then we can have a cut here. When, for example, this cut here, we have the momentum on both directions, like angle theta and phi here, and this is a cut on the Fermi level here with energy 0, and we have the dispersion or the momentum dispersion of each sample here. And when we do this on the Fermi level, we can retrieve the Fermi surface of the sample that we are measuring here. Another thing that we did is that we used the slope of the metallic states on the band gap to calculate quantities like the electron group velocity and the effective mass of the samples. Here we took the cone here, and using the quantities that we measure here and some formulas here, we can retrieve the Fermi momentum of each sample and the group velocity of 6.2 and 6.6 from bismuth selenide and the quaternary sample. And from that, we measure that the electron effective mass of the quaternary sample is 2 times smaller from the bismuth 2 selenium 3 sample. So the conclusion that we got from the ARPES result is that the antimony and tellurium reduces the effective mass of bismuth selenide. The last project that I will present uses a little bit more the powerfulness of the photoemission spectroscopy, which is the topological states on the CDW compound tantalum tellurite. For the ones that don't know what is a CDW is a charge density wave. A charge density wave works like imagine that you have a one-dimensional crystal here with a lattice constant of A, and then there is a lattice distortion on the sample that some atoms move positions here, and there is now a new periodicity on the crystal. What happens is that here you have the band structure of the system without the charge density wave. We have, for example, here you have on green the states that are occupied, and in red the states that are non-occupied. And here we have, for example, a metallic sample. But when we change the periodicity here, the band structure acquire a new periodicity here, and we can now depending on the number of states that are occupied here, that it can open here or another energy gap here that we'll call the charge density wave energy gap. So we can the charge density wave can change a sample from a metallic to an insulator and the other way. So tantalum tellurite is a material that we can see a charge density wave because the structure of tantalum tellurite is composed of linear chains here of tantalum that are surrounded by tellurium atoms. What that's created is the structure here that is formed by that's formed by what we call these linear chains here, and this forms what we call the quasi 1D structure here. So we can see the effects of the charge density wave. So in the first here's the first Brillouin zone of the material. It's important to understand this Brillouin zone because when we cut the material, we have access to two directions here on the surface, which is one direction is related to the direction that is perpendicular to the chain, and one direction is the parallel to the chain. Before I show my results, I need to talk that the experimental background on the sample shows different conclusions on tantalum telluride. The first is that this works here on resistivity on tantalum telluride shows that tantalum telluride should have a topological insulator behavior, because if we look here on the density over temperature of the material, we can see that for low temperatures here, we have what we call the resistivity plateau at low temperatures. This is the signature of a topological states on samples, and also here we have that now we have for low temperatures, and we change the magnetic field here, and we can see that there are quantum oscillations also at low temperature. And when we fit these quantum oscillations here, we can have the information that we have this sample should have a two-dimensional Fermi surface. But the previous ARPES experiment did on this sample, they show a different result. Remember on the Brillouin zone of the sample, these kind of samples that have 1D that have 1D linear chains here. One thing that we should look at is that on a regular sample, on a metallic sample, because of the Fermi-Dirac distribution, next to the Fermi level here, we have what we call a Fermi edge cutoff here, because of the Fermi-Dirac distribution. And then this from this kind of sample, when we have a quasi 1D crystal, we have the both combinations, what we call the 1D and 3D spectral signatures of in the same sample, which means that we have the Fermi edge cutoff here, but we also have a exponential decay of the spectral of the photoemission intensity here closer to the Fermi level. So what that creates is a region here, what they call it as a region of reduced spectral weight on the on approximately 0.3 to 0 to the Fermi level. So, but the thing is that when they look at the states here, this photoemission intensity here, they didn't observe states crossing the Fermi level, which is opposite what was expected from the resistivity results, that they imply that they should have topological states crossing the Fermi level. So our ARPES results, we did ARPES with sequent on light. And here we have an example here of an ARPES image here taken after this crystallograph, this reciprocal direction here, gamma X, and we saw here what looks like a band gap here. But then when we look closer here, we can see that there's the region of the reduced spectral weight. It's here. We have the Fermi edge cutoff, and we have the exponential decay here. But the thing is that on our experiments, we try to look on directions different from the main directions here, gamma X and gamma Z. We went to the ZR direction here, and like the other results, we didn't see states crossing the Fermi level, but when we went to this this direction here, we can see that there are dispersive states crossing the Fermi level. And these Fermis and these dispersive states looks very similar to the Gerais cones of the topological insulators, which makes a connection of the both results that are different from each one, the previous results. Other ARPES results that we did on sample that shows the capability of ARPES to this kind of samples. We are able to retrieve the entire 2D Fermi surface of tantalum telluride when we did a lot of images of different positions of QI, and we retrieved the Fermi surface here, and we can see that we have 4 Gerais cones here on the edge of the first brilliant zone of the material. Another thing that we did on this sample is what we call the KZ dependence. The KZ dependence that we know that the momentum, the perpendicular momentum inside the sample does not conserve as the perpendicular momentum. Is depending on this quantity here. And when we go to a position of the sample, when this angle theta is 0, which is the gamma position, what we call the normal emission, if we go to this position, this number here is equal to 0, and the relation between and we can have a direct relation of the Kz momentum with the photon energy here. And that's what we did. We measured for different values of photon energy here, and we can see that this the states are present in even when we change the photon energy. And then this is the image of when we do this formula here. This is the image that we got when we have the relation between the momentum kx and kz, the perpendicular momentum here. Here is the dispersion obtained on the Fermi level here because of the region of reduced spectral weight. Here we can see nothing here, which was expected. But when we do cuts like on 0.5 binding energy here and -1 binding energy here, we can see here that we have states here. And the thing is, when we saw the Kz dispersion here, there is no dispersion in Kz. The states looks also the same as we change the Kz. What that means, when we have a 2D state, the 2D state doesn't have momentum on the perpendicular direction of the sample. It means that if we have a sample that are not dispersion on Kz, the states that are not dispersion on Kz should be 2D states, which means that these Dirac cones here are 2D states, as in the 2D Fermi surface, which classifies as a topological material. Actually, this is not a topological insulator, it's called a topological semi-metal. So we got on the end of the presentation. First, I want to present the group of the nanoscopy OHV on UFMG when we do the STM experiments. He's a Professor Rogério Paniagua, which is the leader of our group, and Professor Angelo Malaquias, which is also a leader of the group. And I want to thank the financial support from the Brazilian agencies, CNPq and CAPES, and the French agency CNRS, and also the financial and experiment support from UFMG, the Institute of Molecular Science of ORCE, the Microscopic Center of UFMG, and the Universidad Los Andes on the collaboration with Professor Paula Giraldo, and also the synchrotrons that we did the measurement, the Brazilian synchrotron and the French synchrotron. And also thank you very much for hearing me on this presentation and for participate. Thank you.
Okay, thank you very much for the talk. Paula, entonces, Paula, ¿me oyes?
Thank you very much, Pedro. Sí, ya.
No,
Perdón.
entonces,
mi
adelante
computadora
con manejar las preguntas si quieres.
Perfect. Does anyone has any questions for Pedro? From the students? Pedro, while they get the spirit to ask questions. So I have a question about the bismuth, antimony, selenium, tellurium.
Yeah.
Why did you choose to double dope that compound? What was the reason? Because the antimony selenium, antimony 2 selenium 3, this is not a topological insulator, right? So why is there a reason why you chose these two dopings, and particularly the antimony one?
Yeah, the thing is that we can find a lot of works on the literature about when we have 3 elements instead of 4. And here, for example, here we can see the effect of selenium and tellurium, and here on the bismuth and antimony, and they have opposite effects. When one of them moves the surface states, the other one moves the valence band. And we are trying to find a specific doping when we can achieve, for example, if you look here at bismuth selenide, a topological insulator should have on the Fermi level the states crossing the Fermi level. For example, here is an actual topological insulator. Here is not, because you have the conduction band here on the Fermi level. For example, here is also not, and we're using the both these 4 elements to have a surface here when we can have when we put antimony, we lose the effect of the topological insulator. But when we put tellurium again, we can retrieve the curve here, and now we have a topological insulator again. That's why we try to use these different effects to see the amount of quantity of each element that we can use that it can be used to retrieve what we get before.
I see. So you wanted to move the Fermi level to the Dirac cone level, right?
Yeah.
So then brings me to my second question, and is that in your STM measurements, you said that your spectra in your spectra curve showed some signatures of the topological insulator, but if you're not right at the Dirac cone, so what do you expect to observe there in your tunneling spectra? Because in the bismuth 2 selenium 3, you are on the conduction band, right?
Yeah.
So yeah, that was my question.
Yeah, the thing is, if we have an insulator here from the conduction band and the valence band here, we should have any states here, and on the density of states, it will look like a new, like a structure like this, because there is a gap here, a region with when the Idv curve is 0. But if you have these states here and this state is linear, we should have a structure like a V here, which what we're seeing here on the bismuth selenide. So the best way to see the Dirac cone is using ARPES. But if you do have the Dirac cone inside the bulk the bulk band gap, you should also should see a V curve here, like on the graphene here. You see, you have this V here, which is from the Dirac cone of graphene.
I see. In my last question, and then I think Carlos has another question. So The 4-5 phase of the bismuth selenide is a metal. It is not a topological insulator, or is it?
No,
also?
no. I did put on the presentation, but we did the DFT calculations on that, and it's not a topological insulator.
I see. Okay, thank you. That's it. I think Carlos had a question.
Yeah, thank you. Can you hear me?
Yes.
Okay. Well, thanks for your very nice presentation. I really enjoyed. And I have a very simple question. Actually, you already answered some of my question, but let me ask you about the disorder. So you showed us compounds in which you have a very high degree of disorder, and I'm wondering what is the limit in which you started to lose the topological properties. So we know that in principle, TIs are robust against the disorder, right? However, I know that in some limit, you can start to change that property. And I'm just wondering if you have some measures or of the degree of disorder, so you can comment on that, please.
Yeah. So what we observe is that, for example, we have here bismuth selenide and bismuth telluride. What we expected from these works here is that when we put selenium here, or not on the bismuth telluride, but on bismuth selenide, bismuth selenide is not a topological insulator. And when we put antimony on the bismuth selenide matrix here, the sample start to change its structure to sorry if I can make a mistake here, but it goes from an orthorhombic to an orthogonal to a rhomboedral structure. So this loses completely the topological insulator behavior of the sample. Mm-hmm. So what we observe is that just even if you put a lot of antimony on the structure, even if the antimony is equal to the bismuth quantity or amount, when we put just a little bit of tellurium, the sample starts to become a topological insulator again. So what we observe is that the effect of the tellurium, if you have the same amount of bismuth and antimony, the effect of tellurium, it tries to is pretty much stronger than the tellurium on the topological insulator behavior. This was kind of expected because the bismuth telluride here is much more, the state is much more robust than the bismuth selenium sample.
Yeah, you usually have a very high spin orbit coupling, so it has a very
the spin orbit coupling increases a lot when we change the.
It has a very big band inversion. Let's say a very robust band inversion. But actually, I think that both of them are rhomboedral, antimonide selenium and bismuth telluride.
I saw it because I don't remember the type of structure, but the thing is, this structure here, when we put antimony, the atomic structure changes. That's why the topological feature is lost. The structural change.
Do you grow these materials in the university or do you get this from other group?
No, we grow on FMG.
Okay.
Not we did. This is not our work. We just grow the bismuth selenide, and we grow bismuth telluride, and we grew some tentatives of quaternary samples. That's one.
The last question is the following: we know that sometimes this P-type doping comes from the tellurium vacancies, right?
Yes.
And do you know? I mean, do you have a kind of metric to say how big is this effect of tellurium vacancies? I mean, how many vacancies maybe do you have in a large unit cell or something like this?
The thing is, bismuth selenide, when we do the calculation here, the the Dirac energy here should be at the Fermi level.
Uh-huh.
It's not on the Fermi level because of that, because the selenium vacancies here on the sample.
Mhm.
That's the problem to measure the Bismuth Selenide. So that's another thing that you are pursuing when we grow this sample, because you are trying to have what is a real topological insulator, with the Fermi level on the Dirac cone.
Do you remember how much vacancies do you have in this kind of compound?
On Bismuth Selenide, I know that you can have the absence of selenium, you can have the absence of bismuth, and you can have the selenium on the position of the bismuth and the
Yes,
around.
but I mean in the real.
When we
the
put
real
all
compound.
these elements, I don't have an idea.
Okay, got it. Well, Pedro, very nice presentation. Thanks a lot for sharing with us.
For the questions.
Okay, does anyone have another question? If not, then I would like to thank Pedro for your wonderful presentation, Pedro, and we hope to see you soon at some point.
Yeah, I will be very happy to go there.
Yeah,
Okay.
that'd be great. Okay. Thank you.
Okay, thank you.
Thank you, guys.
Bye-bye. Bye, Pedro.